Hello, Dr. Kern.
Hi.
I can, yeah, so I can give a brief introduction of
Absolutely. Please.
Yeah. So, yeah, Dr. Kern is a physician professor, and he is also a co-founder of Munich Leukemia Laboratory, which provide a complete diagnostic service for hematological neoplasms. He's head of flow cytometry department, analyzing more than 50,000 samples per day, which is quite remarkable numbers compared to our local labs. So Dr. Kern has been also very involved scientifically in the advancement of flow cytometry with focus on MDS, AMI-MRD, as well as in the application of AI and the machine learning. He has co-authored more than 300 papers in peer-reviewed journals. Dr. Kern is also a very active member in the international clinical lab community. He is heading proficiency test programs and serves as inspector for ISO 15189 accreditation. And he is also senior counsel for quality at International Clinical Cytometry Society and chair of quality and standard committee. So over the year, we can see the application of AI and machine learning in clinical lab has been very hot topic. But we see like increased number of papers and published on this topic. But Dr. Kern's group is one of very few that brought refined products into the clinical flow cytometry lab that help in day-to-day diagnosis. So which makes him a very unique person whom I'd always like to hear and learn from. So without further ado, please, Dr. Kern.
Yes, over to you, Dr. Kern.
Mm-hmm. Yeah, great. Thanks, Suhai and Michael, for kind introduction. And I will first try to share my screen. So you should see my screen right now, right?
Yep, we see it.
Okay, great.
Good.
Thanks. And so I've been asked, and I try to do this to refer to the use of machine learning and AI and hematologic neoplasms in the pathology lab. So, of course, you know, I'm related to flow cytometry, but as I just said, we have the whole spectrum of diagnostics in our lab and try to apply artificial intelligence anywhere. So I will show you some data from each of them. But please forgive me if I focus a bit more on flow cytometry as compared to the other methods, of course. So this is regarding automation and use of AI and machine learning in a way is also an automation, but not the physical automation which we see here. And in gray is the amount of samples in the flow department we've been pipetting by hand. The blue one is the first automation system we had, and the red one is the most recent automation system. And this is the physical automation. I would just like to refer to, because we do a holistic approach and try to automate anything. And this is just to give you an impression of the automated pipetting we do. So what we do is to place here the patient samples in and place here, or as you see on the next slide, which is a video, the antibodies which are in dried format and which will be brought into solution, and then everything is pipetted like by hand, but it's fully automated with centrifuge on deck. And what we get out is 48 well plates, which we can directly then put into the flow cytometer for analysis. So we try in the wet lab as well, and we can later do in the dry lab to automate. And you can see here it's quite a sophisticated system handling 4 platforms, and we have a movable arm which brings the plates in this example, the antibody plates from one platform to the other. You can see here in front, plates are barcoded. So we draw very much attention to automate, and part of that, of course, is the use of barcoding. And this is then our first automata room. At the moment, we have 10 systems which are capable of 21 colors, which we operate in routine diagnostics. We apply 10 color panels, and we're just switching to 16 color panels. They are in the process of validation. Again, another aspect of automation. You can see here what drives us to take care of automation, which is increasing sample numbers. You see here on a yearly basis, the numbers of samples being analyzed by the respective samples, most frequently, or so-called CLL or B-cell lymphoma panel, which is always about half of everything we do, but also in any other panel, we see increases. And we do not only, as just shown, have to take care of dry lab automation, but maybe also try to aid also to automation of data analysis. And so we calculate that manual evaluation per case on the technician and scientist side costs a total of 10 to 30 minutes. So about 165 minutes per day per person for analysis at a given year, where we calculated that. And we estimated that by applying machine learning models and manual inspection, which is the aim we are targeting, would reduce the work time per case, and also then the overall time to spend for the same person for diagnostics. This is has been a question from a recent CITO workshop where we asked which of these is the most looked for benefits of machine learning approaches to aid clinical data analysis. And basically, I have to confess, I probably would have decided for more than one. Of course, one aspect is reduced variability and accuracy and increase accuracy of manual analysis. Another one is to reduce the time it takes to do manual analysis, as we've just seen. Some thoughts on basic principles of AI and machine learning. So artificial intelligence refers to the general ability of computers to emulate human thoughts and perform tasks in real-world environments. And machine learning refers to the technologies and algorithms which enable systems to identify patterns, make decisions, and improve themselves through data. And machine learning is a pathway to artificial intelligence. And this basically consists of a set of data, the construction of an algorithm, the training of the algorithm from which inference is derived, which can be used. There's three basic types of machine learning approach: supervised learning, unsupervised learning, reinforcement learning. And supervised learning is trained on labeled data sets. Algorithm learns to map inputs to the correct output. Supervision consists of algorithm adjusting its health. And examples are classification of blood cells or X-ray image to detect lung cancer. Unsupervised learning is characterized by being trained on unlabeled datasets. Algorithm learns to find patterns or structures on its own. Aim is to understand the underlying structure or group similar data points together. And examples are clustering of phenotypes in flow cytometry or clustering of genomic data. In the reinforcement learning, here an agent makes decisions by taking action to maximize accumulated reward. The agent learns by interacting with its environment and receiving feedback. And examples are digital health assistant learns how to remind a patient to take medication based on treatment response. And there are, of course, limitations to these approaches, and there have to be ethical considerations. Data quality is much important, and bias. AI is only as good as the data it is trained on. So this applies to any analysis someone does. Labels should be free of human bias, which sometimes is a challenge. And the AI pipeline needs to account for underrepresented or missing data, which is important statistically wise. Then transparency and explainability are important aspects. Openness of AI systems, data sources, algorithms, etc. Black box problem, a good model keeps its secrets, but at the same time, it has to build trust with users. And if the user can somehow understand what the AI system does, its acceptability will be better. And then there are ethical considerations regarding patients' privacy, human interaction, liability of malpractice, and of course, job displacement, which in fact is, at least in part, a challenge, letting people work on reducing the work they have to do, because if no additional work will be there for them, then they may fear they lose their jobs. It has not happened in our laboratory due to the increase of sample numbers, but overall, for sure, this is an aspect to be considered. As we just heard, artificial intelligence in publication is steeply increasing since about 5 years, as you can see here, more and more publications. And I would now like to turn to flow cytometry. This is data derived from our 9-color B-cell lymphoma panel, displaying different immunophenotypes, as all of you dealing with flow cytometry are familiar with. And this is from the first analysis we did, where we thought this should be automatable. We did data reduction by building self-organized maps, which are two-dimensional in addition color-coded, like seeing here in this plot in blue, the CD19 positive B cells, and here, in addition, the characteristics of having CD45 positive activity and no side scatter signal. And even here, you can see by this reduced data kappa and lambda populations. We used these sums to train the first networks, and then build a classifier. We began with lymphoma or no lymphoma, then with CD5 positive and negative lymphoma, and then with the different lymphoma classes. This was based on some more than 3,000 cases with a 2-tube analysis. And you see here the different diagnoses. Most cases were CLL and no lymphoma, but also many other lymphoma entities have been represented. Importantly, in this approach, we had to exclude samples with a low degree of infiltration, below 1%, because we quickly observed that this approach would not be capable of identifying these small populations. So data included were from about 800 cases which were positive at least 1%, and 2,500 cases which were negative. And then the readout has been to provide a probability of a diagnosis, which then in clear-cut cases is near 100% and very low for the other classes. And for each case, and we kept this, we calculate per case prediction probability, which indicates the likelihood the system assumes to have achieved in this single case. And we only analyzed, we only evaluated cases with a prediction probability of at least 95%. And when we just try to predict presence of lymphoma or not, the accuracy has been 99.7%. And as we see here, as we referred to earlier, the true class has been predicted as negative, and the majority of cases have very low degree of infiltration. So for sure, an issue of sensitivity of this method. And then there were a few cases which were normal, but by the system considered marginal zone lymphoma, which is at least very similar, but differing, of course, in light chain restriction. And this is a case, as we see here, which has clearly no light chain restriction that has been misclassified. We added then at the next approach separation between CD5 positive and negative lymphoma cases, and there were only two additional cases being misclassified. True class being CLPL and CLL, each predicted as LPL. And as you can see here, these cases, in fact, have a CD5 expression, although very dimly so, and had an CD79B expression, which may occur in CLL, but is also typical for LPL. So we try to understand the reason for misclassification to be able to work on that. And then we included all 9 classes which we entered into the system of B-cell lymphoma. And still the correctness has been above 99%. And as anticipated, based on the previous analysis, the CD5 positive cases were wrongly predicted among each other, and the CD5 negative cases also. And for example, here, formerly called variant hairy cell leukemia with CD25 negativity had been misclassified as hairy cell leukemia, most probably because of a slightly increased side scatter signal, which is more characteristic of hairy cell leukemia. We then switched to a matrix-based approach, and although, as we will see later, we did still some data reduction, we directly fed all the primary data, so directly the FCS files, into the system. And we started this with about 6,000 samples, and again did these three comparisons. The first one was separating CLL from hairy cell leukemia and no lymphoma. The second one again was to separate CD5 positive and negative lymphomas in addition, and then each lymphoma on its own, and that was in cooperation with Amazon Web Services. We divided cases into training and test data, and again got the readout for each single case with an indicated prediction probability, like 99.6%. We evaluated different classifiers, so-called XGBoost, proof being the best, and importantly here, using again cases or evaluating cases with above 95% prediction probability, including all lymphoma cases, and considering clone size above 0.1%, so 1 log deeper than before, had an accuracy in the first approach of 93%. We then increased that and focused also on other panels we analyzed. So we included a total of 36,000 cases. We're still working on that and improving that. And each panel consisted of cases being positive and negative, a total of 4,000 cases being analyzed for AML, 12,000 cases being analyzed for MDS, 800 cases analyzed for ALL, then B-cell lymphoma, about 10,000 cases, and myeloma and related diseases, 7,500 cases, and T-cell lymphoma, 3,000 cases. And I would like to show you some of the results in a minute. What we did was standardizing and transforming data and rescaling them, then identify expert-based features. And this is what we still do to give input to the models based on what we consider to be important for diagnostics to like drive the model using these features to improve the prediction accuracy. And then we added thresholds for certain markers. We did clustering to identify populations of interest. This is also a topic we're still working on. And then we, of course, analyzed marker distribution of subpopulations, covariance between key markers. This gives you an idea for the different panels we analyzed of the number of features which have been very high in B-cell lymphoma in MDS, but also significant in all the other panels. We then put in this data into the system and applied machine learning, separating the cases between a training set and test set, 80%, 20%, and derived the final or pre-final models. Here again, we used different machine learning models and selected those which were performing best. And our intended diagnostic workflow has been and still is, and you will see later on how we can use it so far to have a given sample, put it in the algorithm, and get the information, yes, there's a lymphoma or no, but not only there's no lymphoma, but also the advice you should analyze an additional panel being this or that, and then derive the report. This is a question also arrived from the CITO workshop I mentioned. Question to the audience had been, which portion of cases predicted at high prediction probability would you consider sufficient to decide using such an AI approach? And majority said it should be successful in more than 90%. So I would have rated even here, for me, it would be very worthwhile to have 50% of cases predicted by an automated approach, which would reduce the amount of needing manual evaluation to half, which would be a significant step forward. But this for sure demonstrate the reluctance so far to really use such systems. And you see here now what we achieved, and we, for the different panels, selected cases based on different prediction probabilities. AML, we used only cases with a very high prediction probability because they were quite much, 82% could be included. And as you see here, the majority of cases have been predicted correctly with a very high average recall of 99.8%. For T-cell lymphoma, we included all cases because, again, those of you who are performing flow cytometry know about the difficulties not to identify populations which have an aberrant phenotype, but to call them T-cell lymphoma or to call them reactive. And this is shown here that the overlap between true and predicted diagnosis is for the positive cases only around 80%. So this is for sure an area which we will have to still work on. For ALL, again, the different subclasses, the majority of cases can be predicted at quite high accuracy, although there's room for improvement, of course. And this, I think, also is interesting, diagnosing myeloma or MGUS, or no myeloma, no MGUS. And you can see that these 38 cases, which were classified conventionally as MGUS, were in part classified by the algorithm as myeloma or as no respective disease. And so, but I think the majority of cases still predicted correctly. So this approach also here is overall applicable. MDS, is the disease most recently introduced because it's, I think, rather the most difficult disease to diagnose flow cytometrically. And therefore also we kind of anticipated that we would start with a rather low accuracy of 85%. You've seen here. We've then focused on the performance of the B-cell lymphoma panel and grouped similar diseases together to increase the accuracy in this large data set, which but still was below 90%. And this is a focus which we are working on. Of course, we would like to have on this graph, you see on the y-axis the percentage of cases with a defined prediction probability. We would have to have all the cases here at 100%, and we would like to have the average recall also at 100%. But as I mentioned earlier, it would be sufficient, in my opinion, to have a portion of all cases being correctly classified, but at very high prediction probability, because this really could save us data evaluation time. And I would like to give you some insights where we're working on now, which is the reduction of complexity. Here you see the conventional expert human review, which is highly complex. And here you see a Tisney plot indicating the pathogenic population, which is AI-based and is easy to understand even for non-expert. Everyone can see this red population, even if it would not have been colored in red. What we do still is kind of the same workflow as you've seen before, in parallel to analyzing acquiring the data, analyze them manually to derive a report. We are focusing on applying automated processes, which include automated gating and also report generation. This is something we've done without artificial, but only human intelligence, but which is our game, of course, to derive from the readout not only the diagnosis like CLL, but also every information which is needed to then write a report text. And one focus, of course, is the identification of light chain restriction. And here you see some examples demonstrating how the algorithm learns how to separate a couple of populations from lambda populations. And this is an example of additional features. So there are lots of features. We've seen this in one of the slides earlier, which have to be considered, which are weighted against each other and connected to each other in order to allow an output of a label and, again, a prediction probability. And this should be an example demonstrating how this can be managed. This will even be automated and fully integrated in our LIMS system. As you see here, the files were drawn into the app and analyzed for the presence or not of MDS. And this have been early data. It's not directly the dot plots what we see here, but very, very similar. So, and we have improved this. This looks now, in fact, very similar to conventional dot plots. And you see here the respective analysis of a B-cell lymphoma data set, which also allows us to automatically analyze this data. And you see here the different diagnoses with the respective probabilities. So this one a case with a not so high prediction probability, and therefore you need the dot plots, as you see here, to manually double check what's the diagnosis to state. We're integrating this now into our LIMS system and will be prospectively evaluating the automated report with the manual report. And of course, we built in like a barrier that you can apply this app only once you've finished your own report. And so it's kind of blinded analysis, and then we see the performance of the AI system. I would now like to refer to cytomorphology. Maybe you have seen such systems in cytogenetics. At least this is where we for years have used these systems. So these are the hotels with frames, each covering 5 slides. This is an automated arm moving these frames here into the barcode reader and then placing them on the microscope table, and then the microscope will, on its own, in an automated way, analyze the slide. And what has been applied to cytogenetics since ages, we have now, as have also others done, applied to peripheral blood smears with the aim of identifying cells, and not only the normal cells, but also the malignant cells, as you see here in a part of the pictures. And we compared in a prospective trial almost 30,000 patient samples, which were analyzed manually, yielding about 3 million manually differentiated cells, and they were compared to 14 million automatically differentiated cells. And overall, the distribution of cells was comparable, and there was a concordance of 94% for malignant and critical cells. We're still working on improving that, but this has allowed us, for instance, also to digitalize this workflow. And at least one technician nowadays can sit at home and just review on the computer the differential, which has been automatically prepared. Here's another example of automated analysis, which is large language model applied to cytomorphology. What we did is having a current case with certain findings and comparing this to historic data. And when we consider this historic data and match them with the differential, our aim was to predict the diagnosis and also to derive the text. And then significant part of this approach has been to look for similar cases regarding the differential count, and then seeing what the readout has been, also taking in account other methods to the respective historic cases. And then we achieved a correctness of about 86%. And also this system automatically then derived the text. And also this is in German. You can see that the header is the same. And I can tell you that the content of the text is also very similar. And basically you cannot judge on which of both texts has been automatically written and which one has been written by a human. And content is essentially the same. So this is another area of integrated automated diagnostics, which will for sure have more room in the near future. Coming now to chromosome analysis, we have been since decades digitalized the workflow of chromosome bending analysis. And while I talk, you see here a very experienced technician doing the digital work they used to do, as I said, for decades. This is separating the chromosomes into single chromosomes, which had not been perfectly done by the software provided by a cooperation partner here. And then the technician will have to manually sort the chromosomes. And so this takes some time. And as I said, she's a very experienced one, and she's able to do this within like 45 seconds. And this was about half of the data analysis time technicians spend on such cases. And you see here a trisomy 8, of course, and you got a feeling it was done quickly, 45 seconds. Here you see what the automated system does now. It's just one click. You don't even have to work on that. And it's a few seconds later, and then you're done with the same job. And we have automated this now that we don't even have to trigger this process, but it's working on itself once the data is on the server. Coming to molecular genetics, before we talk about application of AI and machine learning, I would like to focus on sequencing and whole genome sequencing. So we have standardized workflows for library preparation, sequencing, and data analysis. And we can do whole transcriptome sequencing and whole genome sequencing. These slides, as you see them, become somehow old-fashioned. We're using the Nova 6000, which need 44 hours for one run to do whole genome sequencing. And so we already received the new device, Nova 6X, Nova 6X Plus, which is capable of doing the same and even at higher volume, but only within 24 hours. So this workflow, which is now including data analysis taking about 1 week, will be reduced to about 5 days or even 4 days. And so we have built very near to applicability in routine diagnostics. And what this data can provide is information on copy number variants and also on translocation, because we're combining whole genome sequencing with whole transcriptome sequencing. And this is a rather simple plot with only one translocation, and this is typical for CML, as you know. And other disease types can be identified based on these patterns, like you see here for MPN and CLL, MDS, AML, and the most complex one regarding translocations, of course, BAR, CCA on top, on the bottom right. We can use such data without any further input of other diagnostic methods to try to predict the respective diagnosis, as you see here. And it's not perfect, that's for sure. And one would have to improve on that. But as you see here on the diagonal, the correct diagnosis is the majority. And if we look here to the degree, to the degree of accuracy, it's largest if we combine the different methods, so copy number variations, and also gene expression and structural variants. And this for sure will have a room in routine diagnostics in the near future. We try to apply this. It's difficult because there is diagnostics which are considered standard today, and which are the gold standard and which do all the diagnostics. But as all of you probably know, there are cases which cannot be solved. And we try to focus on these cases and ask our clients to send in samples of patients who have been undergone multiple rounds of diagnostics without any diagnosis to have been identified. And we then did the complete set at our own cost of another time of diagnostics and in addition whole genome and whole transcriptome sequencing. And this was a small sample number so far, but in 1/3 of these cases, we in fact could identify diseases or disease-related changes in these patients which were not identified in any diagnostic features before. And with that, I would like to conclude in asking how do we proceed? I think it's important to spread knowledge and infrastructure. So spread knowledge, hopefully is something we are doing here, and I'm looking forward to the discussion. And we need infrastructure. So for sure, if we talk about applying artificial intelligence, it's not easily done. So we have built up a team and have now 6 data scientists. The one heading the team came to us from AWS, and we've seen the need to intensively cooperate with them to get to such results. And we're still on the way. And also regarding diagnostic technology, of course, we need the respective infrastructure. And this includes, which I have not referred to, cloud computing. I think this is something you're familiar with. There would be the need for develop of solutions between point of care and centralized testing. So sequencing becomes easier. My focus, of course, is flow cytometry. This not necessarily becomes easier in the wet part, we will see. But we will observe and do already observe a tendency towards centralized testing, and this will allow for even more automation and applicable application of AI and machine learning. We will need to guide workflows and digital link lab to clinical information, which is important to find connections between new findings which are clinically relevant. So it's essential to really have a link between the labs providing the reports and identifying the findings and the clinical information, which then could derive in new diagnostic standards. And we should be ready to use algorithms and AI to support humans, and you know that citation that humans will not be replaced by AI, but humans using AI will replace humans not using AI, and this is something I'm also convinced of. And with that, I would like to conclude and thank you for listening. I'm happy to take any question. Looking forward to a discussion. Thank you.
Thank you very much, Dr. Kern. That was very fascinating. It's amazing to me as an anatomic pathologist how quickly these things are progressing. And I think I'm happy I'm going to be retiring in the next couple of years, so I don't have to learn all this stuff. I guess, yeah, opening it up for questions. Anyone have a question for Dr. Kern? Tyler.
Yeah, very interesting stuff. And I think like any of these new AI or even, yeah, I guess AI, you could use self-driving cars as like an interesting example in that it's something that's a complex task that traditionally humans have done, and we wonder at what point it's going to become more and more automated and AI driven. And so using that analogy, I mean, it seems like there was like this surge of like, these are the things you can do with it, and this is how good it can be. But then there was this kind of backlash then of like, oh, when the self-driving car makes a mistake, how do you approach that and that kind of thing. And also even just maybe challenges around like standardization. And I think with lab, that's kind of one of the things, because with AI, you don't necessarily know how it's getting the answer, you just know it's getting the answer, and it figures out how to get there. And so how do you see this kind of like progressing, I guess, in the foreseeable future, where we kind of grapple with this idea of like, how do we get this standardized across different labs? Like, it's all well and good for your lab to get these results with your data, but how do other labs kind of, or how do you standardize it? And then also, how do you manage that kind of like potential backlash if mistakes are made and whatnot?
Yeah.
Kern?
Yeah, very important items. So I like the comparison with the self-driving cars, because every time, and we even here in Germany hear about the news when a self-driving car makes an accident in the US. We never hear if a driver makes an accident in the US. We sometimes hear
Exactly.
in Germany. And same is true, unfortunately, for any item humans are acting on, and this includes laboratory diagnostics, unfortunately. But I think we are aware of that, and it's always the question: how do we deal with that, and how are we taking care of improving quality and make our workflows and procedures more secure, the automated ones in the same way as the completely human ones. And I think part of that, I think I focus on, like with the flow analysis, where we have a prediction probability per case. And and this will give us information what the system thinks is the most reliable data. And what are not detailed is that we use this as an adjunct first only. And the basic decision, what diagnosis to state, will still be human. And I think the important step, which I cannot anticipate how it's being done, is to then skip the human and let the system alone make the diagnosis, which is very difficult, in particular for patients, if they're being told the diagnosis has been made out of the computer. It has a chance of 0.001% to be wrong. That would be difficult if you tell the same about the human, the doctor, who's doing the same. It may be considered differently. So, and there's lots of activities. Again, I cited the Cyto Congress. There's a working group who's at least trying to publish papers on how it should be standardized. There are regulations. I'm kind of familiar with those in the EU, and there will be similar activities in the US and also in Canada, of course. And but it's difficult to really foresee where we will be standing in a few years. But what I'm sure of is that it will be used very much more than today.
Yeah, thanks.
Thank you. And Sakara? I think you have to.
Yeah, thank you. Sakara, one of the hematopathologists at Vancouver General Hospital. Amazing talk, first of all. I have a couple of questions, one for MDS and another one for the lymphoid panel. You know, as you know, like MDS, like when they aberrant, it's nothing loud. It's more about a synchronous expression in the certain stage of, you know, maturation rather than Brian Chai, 7 or 56, whatsoever, right? So in order to come up with, like, you know, good detection or confident, like confidence level of detection, so you use the morphology to screen first, or you just go ahead with the flow? And second question is about lymphoid panel. You use Euroflow. Is your panel is Euroflow?
Okay, yeah.
So what I'm going to mention is, sorry, it's like, you know, I train in Toronto, and when we change our leadership, like from regular panel to like Euroflow, there are a lot of additional markers added in order to increase, you know, the ability to detect the abnormalities. And it kind of trade off, because also, like, let's say, like mantle cell, you add 4 additional markers, monocyte, you add 6 additional markers, but you also deal with a lot of normal sample too. So in order to detect something better, either by human or using AI, but there's additional cost in terms of, you know, build a fundamental of detection. So I wonder, like, you know, when you calculate this between, you know, trying to pick out this case out from normal population, how do you contemplate that? What is the right approach? Thank you.
Okay, yeah, let's try. So regarding MDS, so I would cover the routine diagnostics and then also the AI approach. In routine diagnostics, so since John Bennett's publication in 1981, cytomorphology is the standard to diagnose MDS, and that's what we do. But we also do, of course, flow cytometry in cases with unclarified cytopenias. So we have to know flow cytometrically what MDS looks like. And even though flow cytometry is not the gold standard, there are findings which are specific to MDS. And we all know the data congruence between morphology and flow is about 80%. And so we are putting the picture together. And MDS is I think that's what you refer to, a disease which is evolving. And at the beginning, there's one mutation, and then additional mutations are being added. At some point, you see cytomorphologically that dysplasia is present. At some point, you see abnormal phenotypes, which not necessarily correlate over time with each other. At some point, you will see the disease in either method. So we somehow do this in a combined approach, and we directly refer to the other method, pathology and flow cytometry. And this is important to consider when we do the automated analysis. So we have been referring to the flow readout as a standard for the algorithm to be trained to, because you could decide for doing the opposite and take the morphology as a gold standard where to refer to, but we haven't done this, but it's still work in progress. And regarding lymphoma, so maybe it's a good occasion to clarify, even though it's called Euroflow, only a fraction of Europeans are using Euroflow, and we never did. And I think they did some great work, but what you asked is exactly important. What is the additional value of the additional markers having been added, and then the need to stick to exactly those markers. So we have a lymphoma panel which have an overall of 21 markers, and that's good for doing the diagnostics. And I can only tell in the same way as for the humans dealing with that, sticking with the same panel and getting experience on that is also a value for the automated analysis, because you need uniform data or uniformly generated data. And that's what we are doing. And if your question went in the direction of what's the value of additional markers and how can they be justified, I think this is a discussion which could be endless. So we try to apply constant and more limited panels, and I'm not a friend of like doing the double of the markers and stating that we can do better diagnostics for one or the other markers. That may be true, but not for a bunch of markers.
Thank
Thank
you.
you. Zuhai and then David.
Hey, Shuhai here. I just want to ask, like, regarding to training data. It's all like I saw like you guys use like a massive training data. It's always like the more the better. And also, do we have like what's a roughly number that can be like minimal number of training data can be used to have like a reasonable, good enough model?
Yeah, that's a good point. And if you wouldn't have asked that, I would have told you what our informatics people tell, which is, give me for each class 1,000 cases. and we don't have. If we look for aberrant hairy cell leukemia, we are happy to have 150 cases or something, which probably only very few labs worldwide have. And so if it comes down to what is really the minimum, then it's about 10 cases, but then it depends on how homogeneous this class really is. If you're dealing with classes like marginal zone lymphoma, which have a rather variable or bit variable phenotype, you have to have more cases. If it's something very classical like hairy cell leukemia, smaller numbers of cases will be sufficient. But that will be relevant. So what we are aiming for is, once we've established this, all these procedures for us, we want to spread this through any other labs who have to do training, of course, based on the data they have available. And there, it will be relevant if a lab has a total of 1,000 cases or a total of 50,000 cases, because the higher the number, the better it works. But it's difficult to really say, here's the cutoff, and if you don't have more, then it's not worthwhile. I would always try, and many labs have many cases, and this is something I'm looking forward to cooperate there with other labs.
Thank you very much.
David?
Oh, thank you for the wonderful presentation. It seems like whenever there's a big shift in our potential to help patients through diagnostics, HemPath leads, as was the case with molecular diagnostics. One of the things we're all, think about is the need, manpower needs, projecting into the future, and this impacts the size of our training programs. What are your thoughts in terms of what you think the optimal pathology department should look like in 15 years' time? Or would it be 50% populated by physicians and 50% by data scientists? Or what would it look like? What would the impact? Maybe you could take a HemPath perspective. How does the potential of your work and other work like it change what a diagnostic community should look like?
Yeah, it's very difficult, but I would say half and half. It's different from radiology. In radiology, I would assume, and they are further ahead, and from my perception, it's kind of easier or quicker to get to the aim. And at least for part of radiology, I think we can get rid of radiologists, because there are studies out indicating that artificial and machine learning approaches do more correct diagnosis than humans. Regarding HemPath, I'm not sure. I would rather think that many of the diagnoses can be made, or at least be aided by machine learning. And my rough assumption would be not necessarily half and half data scientists and physicians, but the workload may be half and half by both these types of proficiencies.
Thanks.
And Nick?
Right. Thank you, Dr. Kern. That was a great talk. I was wondering about the stability, not stability, but how well these algorithms will perform if, say, if you have a different lab, different fluorogome antibody combination, different instruments, or even with your own lab, you'll need to, like, say, in 5-10 years, change your flow cytometer. Like, would you have to retrain your whole system again with new sets of data to achieve that same degree of diagnostic accuracy?
Yeah, very important aspects. Answer is in partially yes. There's there's a procedure of transfer learning which we applied even during the first set we did, which was built on 9-color panel, and before that, until 2010 or 11, we did 5-color analysis, and we have quite some numbers of cases which we could analyze. And so we transferred the content which we had learned from the 9 colors to the respective 5-color panels, which comprised the same markers but in different combinations. And don't ask me about the details, but this transfer learning was able to generate a respective algorithm applicable to 5 colors without large loss of accuracy. There was still the need to adjust, but you don't have to start at zero. You can use the data you generated on one lab to adapt these algorithms to another lab. And this is exactly what we plan to do.
Thank you. We have one question in the meeting chat that I'll ask, and it's just gone 1 o'clock. So the question, hopefully, David, I think we've cured the fact that we don't get cut off immediately at 1. Is that correct? Good. So the question is, what is the difference between deep learning and neural network learning models?
Oh, that's I've been taught that, but I can't recapitulate this, and therefore I would need now my AI specialist to really clarify this. I could try, but you wouldn't be satisfied with that. And so I told you in the beginning, like the difference between AI and machine learning, but by heart, for me, it's all the black box. I understand the principles by which it is working, but it's important to not do it completely unsupervised, but to really be aware of what we as humans really have learned and define this as features the system should focus on, and then let the AI people apply the correct approaches.
Thank you. Well, thank you again for an excellent presentation. Very interesting. As David Huntsman says, hematology always seems to be leading the way, or hematopathology seems to be leading the way with these molecular diagnostics. So again, I don't know, maybe it's because it's an easy area. No, just kidding.
The samples are easy to achieve.
Yeah.
It's already digitized.
It's already digitized. And enjoy the rest of your evening, because I guess it's what, 10 o'clock there now?
It's not 10 o'clock, right? Yeah, have a great day, and thanks so much for having me. It was a pleasure meeting
thank
you
you very
here
much.
and giving the talk.
Thank you.
Okay. Have a great
Thanks,
day.
Wolfgang.
Bye-bye.
Thank you.
Bye, everyone.